so we can finish this up, and then I've got the exams. So we can pass them out at the end, and you can look at it, see what you did wrong or right. Okay, so let's jump in. So we're switching over now to away from vibrational spectroscopy and rotational. So we started at rotation, and that was the lowest energy difference in the microwave region. Okay, very low energy photons. Then we went to vibrational energy, which was mid IR, was 400 to 4,000 wave numbers, and that was the vibrations of the molecule, which are higher in energy. Now we're to the electron cloud, which is even higher. So this is in the visible region and UV, and so this is, so if the CH stretch, this was on your homework, the frequency of the CH stretch was 3,000 wave numbers. The laser that we use for our Raman experiment, the green laser, is 18,000 wave numbers. So the visible region is 18,000. That's a good number to remember. Infrared, vibrational is between 400 and 4,000. So we're much higher in energy, 4 times higher in energy. And this is in the electronic region of the spectrum. Now, we're not going to be able to just jump right into the molecular orbitals without talking about atomic orbitals. So that's where we're starting today. We're going to just start with the hydrogen atom, talk about the atomic orbitals that you guys already know about, the s orbital, the p orbital, the d orbital, and so on. And so so we're going to review a little bit today about the quantized atomic orbitals and the 4 quantum numbers that we use to describe electrons. So this is our huge setup for the atomic orbitals. We have in the Schrodinger equation, we have that Hamiltonian piece, and the Hamiltonian piece has both the kinetic energy and the potential energy. So this potential energy term for our particle in a box was 0 inside the box. But for an atom, we have an electron attracted to the nucleus. So we have the Coulombic attraction term. So this is the Coulombic attraction that you looked at in physics 2, the attraction between 2 charged particles. We have the distance between the 2 particles. We have the charge, and in our case, it's just the charge of the nucleus because we have a single electron that's a single -1. But then if we have 5 protons, Z will be 5. So we'll have 5 positive charges. The minus charge from the electron comes out front, and so that's why we have this negative sign here. And then we have this business with the permittivity of the vacuum. That's sort of the reduction of this charge effect through the vacuum of space. So that's our potential energy. It should look somewhat familiar. I realize physics 2 was a little while ago, maybe for some of you. But that's the Coulombic attraction between the nucleus and the electron. And then we have the kinetic energy piece, which is this second derivative piece. We talked about this whole Hamiltonian when we did the Gaussian lecture, where you saw all the parts, the nuclei repelling each other, the electrons repelling each other, and the nuclei attracted to the electrons, and so on. Put all this together in a Schrodinger equation, and we get the energies. But we need this wave function. So what's in this wave function? Well, here's our wave function for the atomic, the atomic wave function for the electrons, and it's broken into 2 pieces. We have the radial piece, so that's the distance from the nucleus, and R stands for radial distance. So we have 3 coordinates, and they're spherical polar coordinates, which makes more sense for something shaped like an atom. Okay, you could do this in Cartesian coordinates and maybe put the nucleus at 0, 0, 0, but then your variables wouldn't be separable. So to try to talk about the radius around the atom, you would have some strange mixture of x squared and y squared and z squared to talk about all of those. So this was a well-known problem solved actually way before quantum mechanics, and it was the harmonics of a sphere. So after Newton, when they started developing calculus and trigonometry, they started solving problems for all kinds of things they saw in nature. You know, how stretchy a spring was and so on. Well, this was the vibrations of a sphere. So they had solved those equations long before quantum mechanics came along. So when they looked at this, Schrodinger looked at this and said, oh, I can use the spherical harmonics to talk about the oscillation of the electron cloud, and that's what we get. So the spherical harmonics had 2 quantum numbers associated with it, and the radial distance from the nucleus has a quantum number associated with it. So in general, the number of dimensions you have in a system, that's the number of quantum numbers you're going to have. Okay, like the stretching dimension, you have one quantum number for that. The rotation around X, you have a quantum number for that. And R theta phi, you got 3 dimensions, you're going to have 3 quantum numbers. And so these are our 3 quantum numbers. And then we have an electron that has an intrinsic angular momentum. So it'll have a spin associated with it, a spin quantum number. So we'll have 4 for every electron. So these are our quantum numbers for the orbitals. So let's look at the way they behave. So here's the energy equation that comes out of that Schrodinger equation. And I want to point out something important that, there it is, okay. So let's go back here. So this is our principal quantum number, N, is right here in the denominator. Okay, and even though L is present in the potential energy of the Hamiltonian, L and m sub L don't show up in the energy equation for the hydrogen atom, but they reappear in the multi-electron atoms. So our energy equation, this is the hydrogen atom energies. And let's look at this and compare it to our particle in a box. So we solved for the particle in a box energies, and I always make a big deal out of where's the mass of the particle. It's in the denominator, right? And so if the mass gets bigger, the energy levels crush down and get closer together. Where's the size of the system? The size is in the denominator as well. So if you increase the box size, the energies get closer together. All of your peaks, which are differences between those energy levels, would be redshifted and so on. So you guys already have this sort of intuition related to energy equations and where mass is. But this one is kind of interesting. Mass shows up, this is the reduced mass here. Mass shows up in the numerator. But look at our energy over here. This energy was positive. All of the hydrogen energies are negative. So look where 0 is. 0 is up here at the top. So if I increase the mass, I make the energy more negative. So it's the same trend. It doesn't look the same because you don't necessarily see that minus sign glaring at you, okay? But if I increase the mass, energy drops because I'm making it more negative, okay? Same with the quantum number. In our particle in a box, our quantum number is in the numerator because our energy is positive. But in the hydrogen atom, our energies are negative. So if I increase the quantum number, I'm making it less and less negative. So the most negative it can be is with the smallest quantum number. If I make the quantum number bigger, it gets less and less negative. So you see down here I have n equals 1. That's the lowest one. N equals 2 is less negative. N equals 3 is less negative. So because our energies are negative, having the quantum number in the denominator, still, as quantum number goes up, energy level goes up. Okay. And then as nuclear charge goes up, that's in the that's in the numerator, okay? And that makes sense too. So if I have a bunch of protons and I have an electron on there, it's going to be lower energy because I've got more attractive potential to that. So as charge goes up, energy drops. So the 1s electron energy on a hydrogen atom may be here, and a sodium atom would be way down here because the sodium has 11 protons. And so it's going to drop dramatically. Okay. So now let's look at the radial distribution for that wave function. This is the Slater type orbital. We showed this in the Gaussian chapter. It's like e to the minus r. And so when you look at the wave function, if you were to square that wave function, it would look like the most probable position is at the nucleus. Okay. But when we integrate this, notice we're integrating by this little volume, so a 3-dimensional integral would be integrating along r and along theta and along phi. And so this little volume is a delta r, delta theta, delta phi. And as I get closer and closer to the nucleus, that delta r goes to 0. And so there's this r squared volume element that has to be taken into account. And when you take into account that there's 0 volume at the nucleus for that electron to occupy, the wave functions curve around and go back down to 0 at the origin. Okay. And so that leaves us with a most probable, right here, MP, a most probable radius. For each wave function. And for the hydrogen atom, the most probable radius is half an angstrom. Okay. So let's compare this to the size of the nucleus. So if we were at Target, my kids were walking with me and I said, look, what about that red ball? If that was the proton, how big would the atom be? So if this is 1 meter, roughly 1 meter wide, the diameter of a proton is about 10 to the minus 15 meters, so incredibly small. But if we said it was 1 meter, how big would the atom be? Okay, it would be 71 miles across, or 74 miles across. So that's how big the hydrogen atom would be with that most probable radius, if that ball in front of target was a proton. So when we say that atoms are mostly empty space, that's what we're talking about. Okay. So if you're coming close to, if there's a hydrogen atom in Huntsville, you would start feeling interactions with it in Navasota. Your atom would be probably over in LaGrange and maybe even further away. As you're coming close to Huntsville, the reactions would start when you're in Austin and Huntsville. Like the outer part of your electron cloud would start to touch. Okay, and you start to get interactions. So we talk about chemistry taking place at the valence electron level, the furthest out electrons. So let's look at some valence electrons. Let's go to sodium. So here's all of the different orbitals and their most probable radii. And so here's sodium. It's got a 3s electron. That's its valence electron. And so if hydrogen is 74 miles across, sodium's nucleus is only like about 3 times bigger than that ball at target. So it'd be 3 meters wide. So maybe about the size of this desk. So if this is the nucleus of a sodium atom, its radius would be 971 miles. So that's the valence electron on sodium. And so if this ball here, that little orange dot on Huntsville, is 74 miles, this is 971 miles for sodium. So bigger than Texas. Okay. So you can remember that if a sodium nucleus was 3 meters across, the valence electron in sodium, that 3s electron, would be the size of Texas. Now, one thing we'd like to point out here, these radial nodes. So notice how the 1s wave function does not have any nodes. The 2s electron orbital has a node, a single node there. The 3s has a node. So this is the blue one. It has a node here, and it has a node here. And this is what a radial node looks like. So the inner part of the 3s orbital is expanding while the outer part compresses. And then sometime later, the inner part compresses and the outer part expands. But there's this node in the middle that's oscillating in and out. So when we draw our orbitals, we don't ever draw those, but I just wanted you to know that they're there. So a lot of times we'll just draw an s orbital, we'll draw a p orbital like this and we'll shade one side of it. We could shade or not shade the s orbital, but what we don't typically draw is on the inside there might be a shaded region on the inside. Okay. We just don't ever show it because it really doesn't come into play. There are radial nodes. At the 2s, you have 1 radial node. At 3s, you have 2 radial nodes. What about a 5s? You'd have 4 radial nodes. You understand what radial means? It's from the radius of the nucleus. So going out from the nucleus, that's the radius. And so these are nodes that are a fixed radius from the nucleus. Now, what about the p orbital? Again, these shapes that we draw, these dumbbell shapes, are really trying to represent this motion of the electron cloud. Okay, so let me make this play again here. So this gray circle is the shape of the electron cloud. And look how it's oscillating along the y-axis. Oops, go back. See, it's oscillating towards the y-axis and then in negative y. Positive y and negative y. Let me do it again. Look at that circle. So positive y is orange, and then when it goes to the negative y, the negative side is orange. So if we were then to plot this in terms of the spherical coordinates, if we plot it along theta, what point, like if I'm on this axis here where theta equals 0 and 90 degrees, etc., as I'm plotting it at 0, the distance that it deflects right here is 0. But if I get to 90 degrees, it's deflected the most. If I get over here, this distance right here is about half of the maximum. And then it goes back to 0. So I would be plotting this circle like that as I go around. I'm plotting the deflection from its average position. So you see, this is the largest deflection, and it's 0 at 90 degrees. I mean, it's 0 at the top and at the bottom. And then over here, it's got its largest deflection, about half largest here and here, and then 0 at the top and the bottom. So since those are negative numbers or positive numbers, whenever I take a snapshot of this thing, I have to change the color to represent the deflection from the average position. So when we draw this as, say, a negative and this as a positive, we are not talking about electric charge. We're talking about its position relative to its average radius. So if the cloud shifts this way, this radius has shrunk. So that would be a negative. This radius has expanded. So that would be a positive. And then sometime later, they switch directions and it shifts that way. And so now this side would be positive, this side would be negative. So when we draw the positive and negative sides of a p orbital, we're talking about the deflections of the electron cloud. Where's the deflection the greatest? Right here. It's the greatest along the y-axis. And sometime later it'll change color and it'll go the other direction. So it's moving along the y-axis. So that's why we call this the 2py orbital, because it's oscillating on the y-axis. We could do the same thing with the z and the same thing with the x. So there's 3 of those p orbitals. So let's talk about the quantum numbers. These s, p, d, and f orbitals are part of the L quantum number. We have the principal quantum number, which is n. And I put a big star on this page. I want to star it again. This is your key for all of the quantum numbers. So mark this page, memorize it basically. N starts at 1, not 0. So pay attention to how it starts. It goes up to infinity. We don't even get anywhere close to infinity, but there's no theoretical limit to how high it can go. Okay. Notice L. L starts at 0. And look at the maximum. This is something that people just, I don't know, students really struggle with this. So when I drew this little symbol here, that's a little eyeglasses. So I'm saying eyeglasses, look at this. There's a maximum to L. It's always n minus 1. So whatever n you pick, if you pick n equals 4, then the maximum L you could have is a 3. If you pick n equals 7, the maximum L you could have is a 6. It can start at at 0 and go all the way up to 6, but it can't go to 7 if n equals 7. It has to be 1 less than n. Now, when we're dealing with all these numbers, they've come up with a scheme to make it a little easier to keep track of. So for the L's, they've given them letters. So this is the S, P, D, F. It's the L quantum number. So that makes it easier to keep track of. Instead of having a 1-1 orbital, okay, or I'd say a 1-0 orbital, we would have a 1s or a 2s, something like that. You know, we would have, instead of using numbers, we would use a number and a letter to keep track of that. Okay, so we could have a 2-0 orbital. A 2-0 orbital would be a 2s orbital. Then we have the magnetic quantum numbers. And look at these. These are also bound. So the smallest value is minus L. The largest value is L. So if L equals 0, I have 0 as the smallest number and 0 as the largest number. So I have 0. That's it. M sub L is 0. If I have a 3, then the smallest number is negative 3 and the highest number is positive 3, and I have all of the numbers in between. So that's pretty straightforward. This gives us those individual orbitals like the p, x, y, and z. If I have a p orbital here, L can be minus 1, 0, and 1. So I have 3 p orbitals. And that's how come I have those magnetic quantum numbers. It tells me there's 3 p orbitals. And then I have electron spin. So this would be the intrinsic magnetic field of the electron. So they call it spin because a magnetic field is generated by spinning charged particles. A charged particle going around a curve would generate a magnetic field. I wish they would have called it the electron magnetic quantum number instead of spin, because we can't detect if it's spinning or not. It doesn't even have a detectable radius, so it's not like a little particle sitting there spinning. It does have a detectable magnetic field, but they called it spin. So anyway, I wish they hadn't. Now, we've got all kinds of numbers here. We can use the N quantum number to bind L. Then we can use letters for L. And then these will be subscripts written on L. And then the electron, in order to use a shorthand, we'll just use arrows. So an up arrow is a positive 1/2 spin quantum number, and a down arrow is a minus 1/2. So when we're talking about the arrows, that's actually a quantum number. So when you draw an up arrow, you're saying the quantum number is plus 1/2 for that electron. You draw a down arrow, it's minus 1/2. So those are our 4 quantum numbers, but we have different symbols for some. We use letters for L, and we use arrows for the spin. So let's look at the notation. This is our notation, our scheme for keeping track of all of the different quantum numbers. So our principal quantum number is the number that we use, and L is the letters, lowercase s, p, d, or f. We could have G and H and I and so on for the excited states, but for the ground states, we only go up to F. And then for a specific orbital, we specify M sub L. Now, we could put the actual M sub L there, but sometimes we will look at the coordinate system in the room, and our room is XYZ. We would say our experiment or our room or our lab frame would be a Cartesian frame. And so a lot of times we'll just say X, Y, and Z for the p orbitals. But it doesn't really correspond to minus 1, 0, and 1. The atom could obviously orient, and then the 0 would be along the X, and the plus 1 would be along the Y or whatever. So we don't always have X being M sub L minus 1. But those are the 3 M sub L's we have, and we just place the atom in our lab frame and call one of them X, one of them Y, one of them Z. So these are our quantum number designations. We use like I said, the lab frame or X, Y, and Z for the P's. And then for the D orbitals, we have combinations of those. So for the 5 D orbitals, we have the dxy, and it's x times y. And let's see, we'll figure out. I'll have to draw that for you. And this is the dx times z. Let's do this one. So let's say this is positive x, and this out here is negative x. This is positive z. Down here is negative z. So why is this x times z? Well, think about what numbers you get if you take positive x numbers and multiply them by positive z numbers. The result is going to be positive. So this will be positive here. What if I take positive z numbers times negative x numbers? This would be negative. All those numbers would be negative. When I go from the positives to negatives, they have to go through 0. So there's a node right there, because I'm multiplying all those positive z numbers times 0x. So right when x is 0, then it goes through 0. Down here, I have negative z values times negative x values, and so the negatives cancel, so this region is positive. And then over here, I have positive x values times negative z values, and so that region there is negative. So this is oscillating like this. So it's growing at the corners while the other corners shrink, and then it's growing at the opposite corners while these corners shrink. So it's doing this. Notice how the p orbital is just oscillating left and right, okay? But the z orbital now has two nodes. I mean, the d orbital has two nodes, and it's oscillating like this. So that's the dxz, or x times z. Look at the x times y, same kind of thing. You've got positive x's and negative x's and positive y's and negative y's, and you have that same plus minus combination. And then the same for the yz, the plus minus combination. Let's look at the x squared minus y squared. So in this case, the x squared, if I square the x-axis, these are positive x's here and positive x's back here. And if I were to square the y's, they would all be positive as well. But if I put a minus sign in front of the y's, I make all of them negative. And so the y's are negative, and the x's are positive, and so that's the x squared minus y squared. And so it's oscillating the same kind of way, but just now those oscillations go right along the axes instead of between the axes. But it's the same kind of thing, positive, negative, but they're on axis, and that's the x squared minus y squared combination. So that's the d orbital. And then this one is really strange. This one is not, they've done a shorthand here in this textbook. They call it z squared, but it's actually 2z squared minus x squared minus y squared. Notice the x squared and y squared have the same sign. And so they're both the same sign, they're both the same color. And so in this case, z squared, so this is positive on top and bottom, and then minus x squared minus y squared. So this is negative all the way around. There's no node breaking that donut. This is also a very strange node because they're conical nodes. Yes? Yeah, so by squaring them, we make them positive. So all the negative x's become positive, and all the negative y's become positive. So we squared both x and both y. And then we've subtracted them. So when we subtract them, we make them all negative. So we have positive values, we put a minus sign in front, and they all become negative. Because the z's are positive, and if we had plus x squared plus y squared, we have a sphere, no nodes. So you could kind of think of an s orbital as x squared plus y squared plus z squared, and that would be a sphere. There'd be no nodes around the like equator or from the poles. Okay, but this one is the opposite combination. We have the plus z squared minus x squared minus y squared. So you could also write this as 2z squared minus, in parentheses, x squared plus y squared, right? So we're taking that x squared and y squared and we're subtracting both of them. So that's what sets up that node right here that goes through the center. Now, this is I don't know how to draw this. So the donut is expanding like that while the poles compress. And then the poles are expanding while the waist shrinks. Okay, so you can think of Earth. The north and south pole get farther from the center of the Earth while the equator shrinks. And then the equator expands while the poles shrink. And that would be a harmonic motion of a sphere. Like if the Earth was hollow and we just had a shell so that it was, flexible, and we banged it on the poles the poles would both squish and the equator would smush out. And then it would shrink and the poles would vibrate back. So that's a vibration of that sphere. So that's what these wave functions are. They're vibrations of the electron cloud. Do they make sense now? You've seen these shapes your whole chemical life. And you never really connected that they're the vibrations of the electron cloud. Just like we have the molecules vibrations, all of its bending and stretching, we have a cloud of an electron around a nucleus, and it's stuck there because of the attraction it has for the nucleus. but that cloud can oscillate. That's what keeps the electron out of the nucleus, is that it's a wave. It's oscillating. It's a standing wave. And I wish I could, get a spherical shell, hang it from a wire, and bang on it with a hammer. And I have a high-speed camera, so I could see these orbitals. They wouldn't necessarily look like this. They would look like this squishiness, right? But if we plotted them around, that's where we would get these shapes. Plot the deflection around theta and you get these shapes. Okay. And then the f orbitals get even crazier. Here's the f orbitals. And then they keep going. Here's the g orbitals. And they have h orbitals and I and j and all of that. They get more and more. And as they get higher and higher in angular momentum, they start to resemble a sphere again. They're just lots of little vibration points on that shell. So here's the n quantum numbers, the L, so all of the L equals zeros have m sub L equals 0, and they're all the s orbitals. So you can have a 3s orbital, you can have a 10s orbital, anytime you have the L equals 0, you have an s orbital. Okay, you have p orbitals here. These only exist when L equals 1. And remember, L is bound by n minus 1. So you can't have an L equals 1 when n equals 1. So that's why the p orbitals do not show up until row 2. So we don't have a 1p orbital because L can't go that high. It can only go up to n minus 1. And if we have n equals 1, you can't go up, to that. Okay. So you only have an L equals 0. You can't have an L equals 1. So for n equals 2, 3, 4, and so on, then you can have p orbitals. So you have a 2p orbital, 3p orbital, etc. You have a 20p orbital. And then same for the d orbitals. If I need an L equals 2, then the smallest n I can have would be 2 plus 1. It would be 3. So that's why the d orbitals don't show up until the third period. Now, why are they on row 4? We're going to talk about that later when we get to electron configurations and the Aufbau principle. Okay. In fact, they might actually be in this notes. So let's look. Okay, so this is just a side deal about the z component of the angular momentum and this magnetic quantum number, the m sub L. We really don't do much with that. It does sort of describe the direction in space of that orbital. The energy doesn't depend upon it unless it's in a magnetic field or an electric field. So if it's a magnetic field, you get some splitting called the Zeeman effect. If you hit it with a strong electric field, you get some splitting called the Stark effect. But then the orbital angular momentum, which generates a magnetic field, and the electron has a little magnetic field, those can couple together, and that's called spin-orbit coupling. So that's when m sub s, the plus or minus arrows, couples with the m sub L quantum number. And we will get into that. So here's our hydrogenic energy levels with L put on them. So for the 1s orbital, we just have L equals 0. For the 2s orbital, we have L equals 0 and L equals 1. So we have 2 energy levels. Okay, so that's the 2s and the 2p. And then for the 3, we have the 3s, the 3p, and the 3d, and so on. But notice how there's no energy difference for the p and the d and the f orbitals. This one is the 4f, etc. So the energy does not depend upon angular momentum in one electron atoms, but that only applies to hydrogen. Okay, or helium plus, or oxygen 7 plus. or uranium 91 plus. So any of those systems, you take all the electrons but one, then this is the energy level diagram for it. And this is a special name, so put a little box around this Grotrian diagram. Okay, so that's the energy level of an atom's electron cloud, is a Grotrian diagram. I guess that's somebody's name, I don't know. But when we get to multi-electron orbitals, then SP, DF have a different energy. So this is how they go. So notice how the two p orbitals used to be here, now they're up there. Okay. And look at the 3s, 3p, 3d, 4s, 4d, 4f, 5s, 5p, 5d, 5s, 5f. So you see how they get closer and closer together as we get up. And so if I'm going to put electrons in here from the bottom up, so the first electrons go as close to the nucleus as they can get, which is lowest energy. Then the next electron goes in here, then the next electron here, the next electron there, there. Now notice I'm on the 3 shell, the n equals 3 shell. So I fill up all of the 3p orbitals, and then I would, since I'm n equals 3, naturally I would think, I'm going to go to the 3d next. But look here, the 4s is actually lower in energy than the 3d. So that's why when we're filling up electrons, and this is how the periodic table was put together, we get to the end of the p orbitals with argon, the 3p orbitals. Instead of going right to the 3d, the pesky 4s jumps in. So potassium and calcium are 4s valence electrons, and then we get to the 3ds. So the 3d orbitals are dropped a row on the periodic table. So even though that says row 4, that's the principal quantum number 4, when we get to the d block, it drops to 3. And then when it gets all the way over to gallium, it goes back up to 4. That's the 4p's. So you should be able to, this is sort of introducing again the electron configurations using the periodic table, and we're going to get good at that. Okay? So the energy does depend upon angular momentum and multi-electron atoms. And so we can build up these electron configurations. So let's practice a little bit quickly. Let's do oxygen. So looking at oxygen, we have 8 electrons to put in here. We start at the bottom. So 1s2, 2s2. So we're now past beryllium. We start over there with boron, carbon, nitrogen, oxygen. So it'll be 2p4. So we're 4 electrons into the 2p block. Does that ring a bell? Okay, good. This should be reviewed. It should be really good. Okay, chromium is a weird one. We're going to look at chromium. It's a D4. So let's do this one, and I'll point out that it's wrong. But anyway, we'll get to the exceptions. 1s2, 2s2, 2p6, because we finished that second row. Then we're going to jump down here, 3s2, 3p6, because we got past argon. And we come in here to row 4, 4s2. And then we should have 3d4. And so this would be the freshman level thinking. Okay, freshmen. Freshers. Okay. Wrong. It is an exception. Okay. And so we'll explore why that's an exception. Does anybody remember why? Anybody covered why? Good idea, or thinking about oxidized and reduced states, but we could do electron configurations for those, but we're at this point still just talking about neutral atoms. So we're not going to change the number of electrons. If we wanted to make a cation, we would take an electron away. And if we made chromium plus, it would look like vanadium. So we'd steal an electron, it would look like vanadium. Okay. How many electrons are in the D block? You can count them up real quick. 10. Okay. And chromium's at 4. If it could have 5, it would have half filled. It would have half the number of electrons that could go in the D block. Now, if there's 5 orbitals in the D block, and I have 5 electrons, I can put 1 electron in each orbital. So each of those electrons has an independent view of the nucleus. And that's great. What about the 4s? It's got 2 electrons in 1 orbital, so they're sharing space. So the s and d orbitals are not that far apart. So instead of sharing space with another s electron, that electron hops over to its own independent d orbital. So it can have its own view of the nucleus. And so that's why the half-filled shells are more stable. Especially in competing with a 4s that's fully filled, that 4s electron is going to just hop chairs and go get its own chair and have, because it's not that much energy difference. In fact, once it does that, everything drops in the atom. It all becomes more stable. Okay. And so this is a cute little meme. Somebody got a picture of the stadium seats and saw the Aufbau principle where they're filling up all of these orbitals. And so anyway, that's kind of cool. So what we just talked about was that chromium is way better because every electron here in chromium in the valence shell has its own independent view of the nucleus. Every orbital is on kind of a different axis and has access to the nucleus with its own wave function. Okay. This is the little tool. You should be able to reproduce this tool, this little scheme. Instead of trying to draw the energy level diagram, this gives you the same answer for the Aufbau principle, where you start here with the 1s, then you just follow the arrows. 2s, and then you come up here, the 2p. Everything's straightforward until you get to the 3p here. So you come up and you do the 3p, then the 4s, then the 3d. And then after the 3d, you're back to the 4p. And then after you get past krypton, you come in on 5s, which is rubidium here. And then after rubidium, you've got the 4ds. See here, 4d. And then you're at indium, you're at the 5p, and then after the 5p at xenon, you come in at the 6s. So these numbers on the periodic table are really useful. Whenever I'm coming off of the last noble gas, I come in here at the 6s. So that tells me where I'm at. I'm at the 6s with cesium. Okay, so we could really simplify things. If we wanted to quickly do the electron configuration for cesium, we could go back to the previous noble gas. So xenon core. Okay, I've now used up 50, I can't read that, 54? Yeah. 54 electrons. And cesium has 55. So I'll just need one more electron. Which one is it? I see the 6 there, so that's the 6s1. That's super. It's so easy using the noble gas core. So just go back to the previous noble gas and grab that. Okay. So we're also, when we're talking about the multiplicity of an atom, and you need this for Gaussian, we had the charge and multiplicity. We're only talking about the unpaired electrons. So how many unpaired electrons are there in hydrogen? Trick question. It's so easy, yeah. So L equals 0, S equals 1/2, and the multiplicity is 2. It's a doublet. It's the number of unpaired electrons plus 1. Okay, and it dates back to how many peaks you would see in the spectrum. So this would give a doublet in an electronic spectrum. Okay. What about this one? Forget all of the paired electrons. We just have one unpaired electron, 2s1. So therefore, L equals 0. It's in an s orbital. Spin is 1/2. Multiplicity is 2. What about this one? Where's that unpaired electron? P orbital. L equals 1. Still spin 1/2. Still multiplicity 2. This is a weird one. So if we're looking at a P5, 1, 2, 3, we have these electrons paired up like this. And I have one unpaired electron. Even though I've got a P5, I've got one unpaired electron. It is in a p orbital, so L equals 1. Spin is 1/2. Multiplicity is 2. So look at all the different ways you could prepare that situation of having a multiplicity of 2. Anytime you have one unpaired electron, you have a multiplicity of 2. Hydrogen, you could have an excited system. So this hydrogen now, its one single electron is in a 2p orbital. So all the electron configurations you've done in the past have been for ground state atoms. Well, they could be excited too. So you could have a hydrogen with its one electron way up in the 2p orbital, not in a ground state. Okay, L equals 1, S equals 1/2, multiplicity 2. What about a d orbital? Well, L equals 2, but still have a single unpaired electron, so S is 1/2, multiplicity 2. What about an f orbital? Let's see, this is how I do it. I start out with a 0, which is a s orbital, like my fist, it looks like an s orbital, right? So s is 0. How many fingers do I have? 0. So I do s, p, d, f. L equals 3. So I see you on the exam, you're like, yeah, 2. And even as a PhD chemist, I still do this just to make sure I don't screw that up. Yeah. So I start with S, that's L equals 0, no fingers. Okay. So I shouldn't see you go, 0. Okay. But anyway, S is 0, so I have an F orbital, SPDF. Okay, that's 3, L equals 3. What about a G? SPDFG, that's a L equals 4. What about a D? SPD, that's a L equals 2. Still, one unpaired electron, spin a half, multiplicity 2. What about this? When I've got 2 unpaired electrons, helium, where I've got an excited state helium. I've got 2 unpaired electrons, they're in 2 different L's. So is L 0 or L 1? Well, we're going to cover that next. Okay, that's the Klebs-Gordon series, and that's the spin orbit coupling and all of that stuff. So we'll talk about that. So let's